In this session, I'm going to look at two major concepts, sampling and estimation. Though they are very much interrelated, probably I would be looking at why sampling is very much required and what do we do as a part of the estimation process. So, on a broader aspect, I'm going to talk about the different needs for sampling as well as different ways in which the sampling can typically be done. Then, moving towards the world of estimation, there is a very important theorem that plays an important role, which we call as the central limit theorem. So I will try to touch base upon that central limit theorem and how would it be helpful for us as a part of our estimation process. Then we talk about the two different types of estimates that we do for the population mean. So we are discussing about the estimation of the population mean and two major estimation mechanisms. One is a point estimation and the second one being an interval estimation. So we'll talk about those two kind of processes, and finally we would try to see what are the typical biases that are possible while doing a sampling. So these are the different things that we have to keep in mind. First of all, so just to get started, see, typically we observe, let's say when I talk about a Sensex or I talk about DJII, Dow Jones Industrial Average, we all know that they are the market indexes, right? They are the market indexes. They are based on the market capitalization of a few stocks which are listed in that particular country. A few stocks, 30 stocks that are listed here, also 30 stocks that are listed. So there is some kind of a calculation that is performed on these stocks, and a Sensex as an index is computed, let's say on a daily basis. Now, this Sensex or this Dow Jones, this S&P 500, none of these indexes, they do not include all the stocks that are listed on that particular exchange. They do not include all the stocks. They only represent a few. But just by understanding those few, sometimes we make conclusion about the entire market. If the Sensex has gone up, we may say the whole Indian market, Indian stock markets are up. So just by looking at the numbers of few of the stocks, we are making a mention that the entire population, entire market is in the upward direction. So that is where we are looking at the companies which are a part of the Sensex or companies which are a part of the Dow Jones as the key indicators of the entire population's behavior. So this is what we call as a sample. Sample is a subset of a population. By doing some kind of analysis on the sample, we are estimating the behavior of the population. By doing some kind of calculations on the sample, we are estimating the behavior, or we are estimating the behavior of the entire population. So that is what is the concept of sampling all about. So here for us the most important things is, first of all, how to do a sampling. So what do we mean by sampling, and what are the ways in which sampling can be done, and how can this sample information, sample calculation, whatever we are doing, how can I use it in the estimation of a population parameter. If I have to estimate the population mean, how can I use a sample for doing those kind of estimations? So this is what is a very important aspect that we are going to look at. So just to get started with the fundamental of sampling. So the intention behind the sampling is come out with information about the entire population or select a few elements of the entire from the entire population using a different sampling procedures and do some kind of a computation. So the computation that we perform on the samples we call as statistic. So use those statistics to estimate the parameter. Parameter is something that describes the behavior of the population. So generally, even when we have a population of the data, we still rely on the sample. Why so? In one case, probably the whole population, I don't even know what is the whole population. And it's very difficult to really get each and every data of the entire population. Or in some cases, though I know what is the whole population, probably the cost that is involved in getting the whole data is pretty expensive. So it's nowhere efficient economically. So by getting into the sampling process, we are really saving on time and money. That's one important dimension of sampling. So when we are discussing the sampling, I talk about two major mechanisms right now, though there are so many varieties of sampling, but the most commonly used ones which are going as a part of selecting a sample at random. So within that we talk about a mechanism called simple random sampling, and the other one is a stratified random sampling. The two are heavily used in the finance industry or for many other industries as well, the simple random as well as the stratified random sampling. Now, when I look at, let's say, my entire population, this is my entire data, and out of them I have selected these values at random, and I have computed the sample mean for these particular values. Taking these particular values, I have computed the sample mean. So whenever we talk about the population mean, we represent it by mu. Whenever we talk about the sample mean, we represent it by x bar. Now, what is the advantage of just collecting this sample? We have already said one, we can save on time, the other we can save on cost. But at the same time, there is a possibility of an error when I have to predict the population mean, because I did not consider all the elements of this population. There is a possibility of an error. So which means this is a kind of striking the balance between the time and cost, versus the error. I may save heavily on time and cost, but it can induce an error. So my intention is to what extent I can optimize this particular scenario, and that is where we are coming out with what we call as a sampling plan. A sampling plan clearly lists out the details about what is the type of sample we are going to go with, what are the rules that are driving the selection of the sample. So when I talk about a simple random sample, it's like this. So I'm selecting a sample, let's say whatever is the size of this sample. This sample is selected in such a way, let's say if this is the population, every element of this population, has equal chance of being included in the sample. Means probably if the population is of size 500 but I am selecting a sample of size 50, any one out of these 500, any 50 out of these 500 can very well be selected into the sample. So that is what we are calling as simple random sample. So every element of the population has an equal chance of being included as a part of the sample. So which means everything is random. The way in which an element gets added to a sample is completely random. So I can use the random numbers which are there as a part of various tools, use the random number generators, computer based or random number tables that are available, use them to randomly pick the X items out of the N items which are there as a part of the population. So that is one way going as a part of simple random sampling. But slightly an improved version of the simple random sampling is the systematic sampling, especially when I'm not able to randomly assign numbers to each one of them and pull the values. What I can very well do is I can follow a systematic procedure. Now that I require 50 elements out of the 500, at random I'll pull out the 10th element. At random, I'll pull out the 10th element 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is included in the sample. This is included in the sample. So every kth number is being included as a part of a sample until we have the sample of the size which we are looking at. Right? So that is a way of sampling which is a systematic sampling. Now whatever is the sample that we have collected, we will compute the sample mean. And what we are saying is the sample mean will provide an estimation towards the population mean. Though I don't know what is the population, though I have taken one subset of that particular population, computed the sample mean, we'll be looking at it slightly later, where we say that sample mean provides a decent estimation of a population mean. And wherever these two things differ, the difference between the sample mean and the population mean is what we are typically calling as the error because of the sampling, and we are treating it as a sampling error. So it's a difference between the observed value through the sample and whatever the corresponding value that we want to estimate for the whole population. The difference between the two is what we are calling as sample error. And whenever we are talking about a random sample, because we are selecting the data at random, all the properties of the population will be represented completely in a neutral and an unbiased manner. That's one of the prime reason we say the sample selection, whether it is simple or stratified, it has to follow a random kind of a process. Then only the behavior of the population will be represented in an unbiased manner. And what we typically have to introduce now is whatever the statistic we are computing, let's say sample mean. The sample mean is not a single value. Let's understand. It's not a single value, rather it's a distribution. The most important driving piece for us here, The sample statistic is not a single value, it's a distribution. It's actually a random variable, because what is typically happening is, out of this 500, depending on which 50 I am selecting, the mean can slightly differ, right? The mean of each of the 50, each combination of 50, the mean can be slightly different. So when I am looking at the means as the different values, the mean is actually becoming a random variable. So which means there is a distribution associated with the means, sample mean. There is a distribution that is associated with a sample mean, and that is what we are calling as sampling distribution. It's not the distribution of the original data, it's the distribution of the statistic. So when I say sample mean is a statistic, there is a distribution that is getting built for this sample mean as well. So all the all the different possible values that the statistic can take. If I'm talking of sample mean is a statistic, all the possible values that the sample mean can take is what we are calling as the sampling distribution, right? When are we talking about it? When I'm taking the samples of same size n from the same population. Let me try to demonstrate that. So let me take a sample data. Here I am taking the a sample data corresponding to heights of people. Here I am taking the sample data corresponding to the heights of the people. Let me take them as formatted. So I have used some formula to randomly generate the heights of the people. Now what I am saying is, I will try to compute the mean of them. So I have how many? I have around 200 people's data. So randomly I have selected some 200 people and I have computed their heights, let's say. Now I am trying to find out the average of their heights. Okay, so now I have got that the height is 164.49. But now when I randomly generate another sample, right, another set of 200 people, I'm getting a mean as 165.69. So let me note down what are the values that I'm getting. 165.69. Now again I'm doing it, I'm getting 165.56. But again 165.48. 164.82. 164.79. 164.49. Right? If I'm which means if I'm changing the sample, I'm getting a different values altogether. 164.88, 164.39, 165.39, 165.6, 165.18, 164.10, 165.2, 163.87, 164.74, 164.45, like this. Now what is happening is, every time I'm changing the sample's mean is changing. But here what is there? I'm taking the 200 elements from the same sample, from the same population. 200 is the sample size, and with that particular sample I'm trying to compute all these things. And what I am seeing is the mean, the sample means, it's not one single value, it's following a value in a particular range. It is taking the some kind of a distribution. It's a random variable and it is taking some distribution. So that is what we call as the sampling distribution of the sample mean. So this is how I can represent the sampling distribution of the sample mean. Alright. Alright. Now the next important sampling mechanism that I want to look at is the stratified random sampling. Stratified random sampling, because in majority of the cases a simple random sampling may not be the best possible approach. The reason being, see, let's say I'm taking a data of people, and let's say there are 70% males and 30% females in the data. Now I'm selecting, let's say out of this 500 people, 350 are males and 150 are females. So let's say when I'm doing a simple random sampling, probably of let's say 100 being the sample size, it may so come that the males are 20 in it and females 80 in it, females are 20, or males are 60, females are 40, or probably it can come to 70-30. Any combination can come because I'm randomly picking up 100 out of the 500. So which means this combinations, they are not a better representation of the population, because I am more interested in understanding the behavior of the males versus the females. So I would like in the selection of the sample also, I would like the entire population to be divided into subpopulations, and from each subpopulation collect a sample in a random way in that kind of a proportion that it represents the population. So once I divide the whole population into the different groups which are called as strata, and from each of the stratum I am selecting a sample in a random manner in a proportion relative to the size of each of the stratum in the population, and after that the data is pooled. So this kind of a sampling will ensure that my sample contains 70 males and 30 females, whereas the simple random may or may not ensure. So whatever the populations, especially if I am more interested in the subdivisions and analyzing the subdivisions of the population, then this is the best method to go with. And what is expected is this kind of a method will give me the highest level of accuracy, a better estimation of the population parameter compared to a simple random sampling, because it gives me a more and more least possible variance. So it can result in whatever the estimation I am doing using this sample, the computation mechanism becomes more and more efficient, right? So this is what typically goes as a part of stratified random sampling. Probably bond indexing, the way the bond index is built, is a very classic example of the usage of stratified random sampling in the financial world. We can classify the bonds based on various groups, probably based on their risk, the interest rate risk measured in the form of duration, or I can look at the sector based classification of the bonds or the credit quality based classification of the bond. So all these various stratum that gets up, I select the bonds on a random basis. When I'm creating my portfolio, I'm selecting the bonds in a random basis from each of these strata in the same proportion as the composition of each of them as a part of the overall bond index. Then I can say that I have replicated the bond index, though not including all the bonds that are going as a part of the bond index. So that is what goes as a part of the understanding of the stratified random sampling mechanism. Alright. Now, looking at the next important concept, the types of data. Whenever we look at any data, we have to see whether it is more of a time series based or is it more of cross sectional based. Right? Typically, we work with one of these two forms of data. So whenever we are looking at collected at any data that we are collecting at discrete, equally spaced intervals of time, then we call it as time series data, especially some monthly prices, daily stock returns, right? All these quarterly growth rates, all these things, if I am collecting at different points in time which are equally spaced and discrete, I look at it as a time series data. Whereas whenever I am looking at a cross section data, I am collecting the data at one point in time, at a particular point. So I can collect the data relating to different people, or I can collect the data relating to different vehicles, entities, kind of stuff, or I can collect the data regarding different countries at a particular point in time, or probably some data on different firms and companies, their profitabilities of this particular year. All these things, whenever I'm computing or collecting the data at one particular point in time, we are calling it as a cross section data. And remember, even in a time series data, there is nothing which says what do you mean by long time period or what is short, or how long a data that I have to collect for doing a time series analysis. In some cases, it could be pretty short. In some cases, it could be pretty long. But it's better that we do the selection based on the requirement. See, if it is too long a data that I have collected, probably intermediately there has been some kind of a change in the practice process. So there is no point in clubbing two unrelated kind of a data. Though let's say both of them are of the exchange rates itself, probably for the last 4 years the exchange rate has been a floating rate, but prior to that, let's say it was a fixed rate. So there is no point in selecting the last 7-year data because 4 years is floating and before that it is fixed. It's better to take only the last 4 years data because they become completely unrelated and whatever the calculations we do on it becomes completely unstable. So we have to make sure that whatever the data that we are collecting, it does not go completely unusually different, just in an intention to select the data for longer time period. So if there is some kind of a characteristic, primary characteristic change or some basic difference that is existing, it's better to take the data only of one relevant period rather than trying to look at it for a longer point in time. So that is what on the time series data perspective, when I'm looking at a cross-sectional data, whatever the data that we are getting, let's say the heights of the people, the prices of the cars, the GDP of the countries, whatever it is, the different data that we are collecting, if at all I have to summarize it in a meaningful way, we generally make an assumption that that particular variable, let's say heights or prices or sales or P by E ratios, whatever it is, whatever the element that we are going to study for the different entities, we treat that as a random variable based on some underlying population try to look at the mean of it, try to look at the variance of it, and try to make some kind of an assessment regarding the distribution of the underlying population. So that is what will become a starting point to our detailed summarization, especially when we are working with cross-sectional data. So generally, again, so from that perspective, if I'm taking almost any country or any sized company, probably the numbers are drastically different. So let's say from an financial analyst perspective, I look at taking the data, let's say industry wise, to make sure that the values are not drastically different. But again, different there could be different ways in which different companies can get allotted to industry. So we have to be careful in terms of defining what is our industry and what kind of companies go as a part of the industry. So once we know whatever is our data, we know that we have a random sample which is a representation of the entire population, and that is where our next step starts in terms of making an estimate of the population parameters. So initially starts off with estimation of the population mean. But before getting into the estimation directly of the population mean, we are trying to understand one important concept that drives or that facilitates heavily the estimation of the sample mean, which is the central limit theorem, a very important theorem which has revolutionized the estimation of the sample mean process. So, what is it all about? We have already discussed earlier that we take a sample of the data, we compute the sample mean represented by x bar, and there could be a difference between the sample mean and the population mean, which we have mentioned it as a sampling error. And at the same time, we have mentioned that this sample mean is not a single value, it's a random variable. So there is a distribution that is associated to this random variable, right? So we are looking at how close is this sample mean to the population mean. What is the kind of closeness the sample mean has with respect to the population mean, and that comes quite comfortable if I understand the distribution of the sample mean. So the distribution of the sample mean is the most important aspect, right? So the distribution of the sample mean is what if I have to look at. That is where the central limit theorem is playing an important role, which simply tells me that let's say I have a population, and let's say the mean of that population is mu, and the variance of that population is sigma square. Let's say I have taken a sample of some n elements. I have taken a sample of some n elements and I have computed x bar. Now what we are simply saying is the sampling distribution of this x bar. So for this x bar, if I am looking at the sampling distribution, what we are saying is the sampling distribution will be approximately, this distribution will generally be a normal distribution first of all. The mean of this normal distribution is mu. The variance of this normal distribution is sigma squared by n. This is what, especially as n is becoming larger and larger, what we are simply saying is the sampling distribution of the sample mean x bar, the sample distribution of the sample mean x bar follows a normal distribution with a mean equal to mu and variance equal to sigma squared by n. So this helps me to really come out with the estimate for a population mean using the sample mean, whatever may be the distribution of the original data. Right? So let's say in this particular example, I've taken a sample of size 200, which I have already talked of. Now, what we are saying is, these are the different sample means that we have got. Okay, so the average of the sample mean, the mean of the sample mean. So this, for this I am taking the average. So 164.91, and the variance of these, is coming out to, this is the variance. So this is the mean, this is the variance. So probably if you look at, let's say this is the entire population, here I can trace the variance. You see the variance here. The variance of this is coming out to 115, and this divided by n, which is 200. So variance in this case is coming out to 0.54. So here we have got it as 0.29, but because I have to generate large number of samples, but what we are simply saying is the mean of this. So if I look at the sample means, so these sample means will follow a normal distribution whose mean is going to be the mean of this entire. So you see here we have got a 164.91, we are getting 164. So the mean is typically getting equal to the population mean with a variance equal to sigma squared by n. So this one will really help. So this is not this is not applicable to the original data. This is applicable to the sampling distribution of the mean only. So the sampling distribution of the mean, irrespective of whatever is the distribution of the population, even if the population is not following any specific distribution, the sample mean of that taken from that particular population of a particular size n is going to follow a normal distribution with a mean equal to mu and a variance equal to sigma squared by n. So if n is becoming larger and larger, the sigma squared by n variance is becoming lesser and lesser, which means the sample mean will be very close to the population mean, and it will not deviate very much from the population mean. So this can help me to provide some kind of estimate, what we call as probabilistic estimates of the population mean by using the sample, irrespective of whatever is the distribution of the population. Because we are making an assumption, or we are making a statement, or central limit theorem is creating a statement, whatever may be the distribution of the original data, the distribution of the sample mean of that is definitely a normal distribution with a mean mu and variance sigma squared by n. So whenever the data is large only, this is applicable, and the definition of the large is greater than 30 elements. Right? So the variance is going to be sigma squared by n, means the standard deviation is going to be sigma by root n. And whenever this standard deviation is computed from the sample, this is what we call as the standard error. So the standard error is nothing but standard deviation divided by the square root of the sample size, square root of the sample size. So either if the population standard deviation is known, I'll compute it as sigma by root n. If the population standard deviation is not known, then I'll depend on the sample standard deviation and I compute it as s by root n. So that is what is going to give me. And we all know that sample standard deviation comes from sample variance, and the computation of the sample variance comes out like every item subtracted from its particular mean, squared, added, and then divided by n minus 1 instead of n. So once we know the standard error, so what we are saying is the population, for a population mean, the estimate is nothing but whatever is the sample mean I have got. I build a small interval around this sample mean, and I say that the typical range for the population mean is between this and this. What is typically looked at is the population mean can be included. I'm not able to say the exact value, but I can say whatever is the population mean, it can lie between this and this kind of an interval. So population mean is still a single value. It's not a distribution. But what we are able to do through this mechanism is, though we are not able to point to the population mean exactly, we are saying that the population mean will lie between this and this. It's one single number that could be somewhere in between these two numbers. So that is what we are able to come out by using the central limit theorem. So just to summarize the central limit theorem, whatever the distribution of the sample mean, first of all, it is approximately normal distribution with a mean mu and variance sigma squared by n. So the mean of the sample means, the mean of the sample means is going to be more or less equal to the population mean. It is going to approximate the population mean, and the variance of the sample means is going to be the variance of the population divided by n. If I have to compute it from the sample, it comes out to be s squared by n. So that is what is in summary the central limit theorem and the sampling distribution of the sample means. Now with this we get into the next important concept, which is the estimates of the population mean. We are getting into estimates of the population mean, where we talk about two major estimates. One is a point and an interval estimate. So when we have to get into it, before that, it's better that we understand that we are now slowly moving into a world of statistics, which is the inferential statistics. So when we talk about the inferential statistics, I talk about two major concepts. One is the estimation process, which we would be talking of now, and two is the hypothesis testing, which we will take up in our next session. So hypothesis testing, generally, just to give an overview, I have some value for a population parameter. So someone might have made some kind of a statement regarding a parameter, and I want to test whether the data that is available with me is supporting this particular statement or is not supporting this particular hypothesis. That's a typical thing that we do as a part of hypothesis testing. Whereas in the estimation, we don't have any value for the population parameter. We are trying to estimate the value for the population parameter. So we use the samples data. We do some kind of samples statistic computation, and based on this statistics computation and the various rules, we are trying to come out with an estimate of the population parameter. So when we are coming out with a single estimate of the population parameter, one single value estimate for a population parameter, we call it as the point estimate. But point may not be realistic in the real term, because it's very difficult to make my point estimate exactly match with the population parameter. So that's where we talk about, instead of a single value, we talk about a range of values that can say that the population parameter actually is lying in this particular range. It is one single value which is lying within this particular range, and I can say this with a particular confidence level, with a certain level of probability, with a certain confidence level. I can say that population parameter, whatever the value of that is, it lies between this lowest and the highest limits, right? So that is what we talk of in the estimation process. So just looking at it, the point estimator, whenever we are talking about the point estimators, first we look at a formula. Whenever I am talking about a point estimation, I am looking at some kind of a formula based on some random outcome of the random variable. So that, let's say for the sample mean, x bar, the sum of all the values of the sample divided by the total number of elements that are there as a part of the sample. So that kind of a formula is called as an estimator. So what I say is sample mean is an estimator of the population mean mu. So sample mean given by x bar equal to the sum of all x's divided by n. So this is an estimator for the population mean, and whatever the value that I am getting, which is x bar, whatever the value that I am getting, I call that as an estimate of the population parameter. So estimator will have a distribution, whereas estimate is one single value. So it is not a distribution. So whatever we are talking of point estimate, so this is a better estimate of the population parameter. So we say sample mean is a better estimate of the population mean. Now what could happen is there could be good number of parameters which could be an estimation of the population mean. There could be a lot of estimators. So probably why only sample mean? Why not a weighted mean? Why not a geometric mean? Any one of these could be an estimator for a population mean. Now, if there are these many estimators that are available, so how do I choose among these different estimators for coming out which one is the best estimator for the population parameter? So this is where people talk about three important characteristics that are associated with the estimators. One, they say that the estimators need to be unbiased. Two, we talk about the estimators need to be efficient. And three, we talk about the estimators being consistent. So whenever I talk about they being unbiased, all we are saying is the expected value of that distribution, expected value of the random distribution, sampling distribution, should be equal to the population estimate, should be equal to the population parameter. So then it becomes more and more unbiased. So what we say is sample mean is an unbiased estimator of the population mean. We say that S squared computed using x minus x bar whole square divided by n minus 1 and not n is a better estimate of the population variance. But when I divide it by n, it does not go as a better estimate, it goes as a biased estimate of the population variance. So that's the reason for a sample variance we always use dividing by n minus 1 because it's an unbiased estimator of the population variance. So when there are so many such kind of unbiased estimators available, if not one, sometimes I may find that for estimating one population parameter, it's just not one, I have many unbiased estimators. If that's the case, then I will be looking at the next important feature to shortlist on which of them is a best estimator. I look at the efficiency. And when I'm talking in terms of efficiency, I'm looking at the sample distribution, whatever it is, the sampling distribution, it generates the lowest variance. Whichever, probably if I am using arithmetic mean or weighted mean or a geometric mean, whatever is the estimator I am using, I look at the sampling distribution that is coming out of it, right? So probably it's like this. In each of these cases, instead of mean, I could have computed even the median also. And let's say these are the values of the median that I have got. I'll try to find out the variance of this. I'll try to find out the variance of this. So whichever of these two is giving me the least possible variance, that will become my estimator of the population parameter. So that is means though there could be many unbiased estimators, whichever the sample distribution giving me the least possible variance, that will be the most efficient one and that would be selected. And the next important behavior is consistency. So whenever I'm talking about consistency, as the sample size increases, as I add more and more values to the sample, the whatever is the estimate of the sample parameter, the sample statistic will keep on coming closer and closer to the population parameter. So the error is getting reduced lesser and lesser. The sample statistic is coming and approaching the population parameter. The standard error, let's say when I am looking at sigma by root n, as the sample size is increasing, the standard error is reducing. And if the standard error is reducing, probably I am seeing that the interval is getting narrowed down, which is resulting in the sample's statistic value approaching the population value quite comfortably. So these are the three characteristics that need to be satisfied by the good estimators. They need to be unbiased, they need to be efficient, and they need to be consistent. Now, once I know that these are the different kinds of estimators that are around, then the next task for us is how do I compute the confidence interval? I know the point estimate, but now I am looking at the confidence interval estimate for the population mean. So whenever I talk about a point estimate, it's actually a single number, probably x bar, sum by total. So it's a kind of a single number. But because of the sampling error that is possible, one single point estimate is not going to match the population parameter to any extent. So that's the reason probably in large number of applications, the range is what we are looking at, which is going to bracket the parameter with a specific level of probability. So what we say as a confidence interval is, it's a range, wherein I can say with some given probability 1 minus alpha I can say with some given probability or 1 minus alpha, or sometimes this 1 minus alpha is even called as a confidence level. I can say with 1 minus alpha percentage level of confidence that whatever the range that I am talking of, this range will contain the parameter that I want to estimate. So I can say that I am telling with 95% confidence level, I am saying that 10 to 14 is going to contain the population parameter. The range 10 to 14 is going to contain the population mean. So this is what I call as the lower limit. This is what is the upper limit. And any confidence interval we are trying to interpret in two ways. One, we talk of the probabilistic interpretation, whatever the representation, this representation. One, we can do it in a probabilistic way. The other, we can do it in a practical way. The probabilistic way of saying it is, if I perform, let's say I'm taking a sample size of 100 from some population. I'm taking a sample size of 100 and I'm computing the sample mean. Let's say I have randomly taken 100 such, I have done this work 100 times. Taking a sample, let's say taking a sample of 50, and on a sample of 50 compute the mean. And let's say I have done this exercise 100 times. What we are saying is, if I am doing this exercise 100 times, 95 times, approximately in 95 times, whatever the sample mean that I am getting, it will lie between 10 and 14. Only in 5 different times, probably the sample mean could go either this side or this side. So that is a probabilistic way of talking about it, talking about the confidence interval. Whereas the practical way talks of more and more important is the practical way, because I cannot repeat this experiment 100 times and there is no point in doing it. So the practical way comes into picture, wherein I say I am 95% confident. So the practical way gets translated like this. I am 95% confident that whatever is the interval we are talking of, this interval contains the population mean. Only 5% I have the doubt that this interval may not contain the population mean. The population mean could be either lesser than the lower limit or greater than the higher limit. But 95% confident that the population mean will be present in this particular interval itself. And the way we are computing that particular interval is based on the point estimate itself. So whatever the point estimate I have got, we talk about plus or minus reliability factor times the standard error. So we have already seen the standard error is computed as sigma by root n, and reliability factor is coming primarily from the understanding of the distribution of the data. Right, reliability factor comes basically from the understanding of the distribution of the point estimate along with the confidence level. So these are the two elements. So depending on 95% confidence level, and let's say my data is following a normal distribution, the reliability factor is going to come up. That is getting multiplied by the standard error, which is going to give me the confidence interval for my prediction. So just to start with, let's say when I am assuming that the sample distribution is going to follow a normal distribution, because to a large extent using the central limit theorem we are able to come out that the sampling distribution is going to be approximately normal, right? So we can very well take the distribution to be a normal distribution, and more particularly a standard normal distribution, wherein I can talk about the interval. Let's say if I'm talking about a 95% confidence interval around the mean, we are talking of x bar plus or minus 1.96 times the standard error, because when I'm talking about 95%, so the 95% is 1.96 standard deviations from the mean. So I can very well say that the 95% confidence interval is 1.96 standard deviations or standard errors. 90% confidence interval comes out as x bar plus or minus 1.65 standard errors. 99% confidence interval comes out as x bar plus or minus 2.58 standard errors. So this is something which are known to us based on the normal distribution pattern. So I can very well take, when I am looking at the 95% standard deviation or 95% standard error, so we can very well find out the z alpha by 2, which is the normally cumulative normal distribution value from this particular point in time. So if I want 5% this and this side, I'm looking at 2.5% value in the tail. So this tail of 2.5, this tail of 2.5, whatever are the values. So this tail of 2.5% will give me minus 1.96. This tail of 2.5 will give me 1.96. So that's the reason we are building an interval x bar minus plus or minus 1.96 times the standard error. So this is how a confidence interval can be built. And of course, now as we are seeing, as the standard error is higher and higher, the width becomes wider and wider. Or as the reliability factor is increasing. Now, when will the reliability factor increase? If I want 99 instead of 95, the reliability factor is actually going up. For 99, we said that the reliability factor is 2.58. But for 95, we said that the reliability factor is 1.96. For 90, we are saying that the reliability factor is 1.65. So the more I am looking at the reliability factor, the wider is the interval. And the more wider I am going on my interval, probably the precision is actually going down, right? So the more and more we are increasing the confidence level, that is what is the reliability factor going up. The more and more I am increasing the confidence level, I am seeing that the interval is becoming more and more wider, and the information is becoming less precise, because I am getting a big interval in which the population parameter is going to lie. So the more and more accuracy we are looking at, the more and more definiteness we are looking at, we are compromising on the accuracy. Right? The more and more definiteness we are looking at in our estimate, the more and more confidence we are looking at in our estimate, we are giving up the precision, and we are allowing more and more of widening of the interval in that case. So as long as the sample size is larger, we have talked about that the sampling distribution is approximately normal, right? But in that case, we are saying that when the population is having a finite variance, but there could be a possibility that the population's variance, in majority of the cases, the population variance is unknown. So if the population variance is known, whatever may be the distribution of that population, the sample mean is going to follow a approximately a normal distribution with a mean equal to the population mean and a variance equal to sigma squared by n. But in majority of the cases, we do not know even the population variance. So, if that is the case, I cannot make an assumption of the normal distribution. So that is where, if at all I have to come out with a confidence interval, especially when the population variance is not known. Especially when the population variance is not known, we cannot rely on a normal distribution. We are following another distribution which is more or less similar to that of a normal distribution, which we call as a student's t distribution. Student's t distribution, or in short we call it as a t distribution. So this is very heavily used in terms of estimations, because majority of the times the population parameter, the population variance is typically not known. So whether the sample size, this is a very common mistake which people make. Whatever may be the sample size, large or small, whatever is the sample size, large or small, as long as the population variance is not known, I'm relying heavily on the t distribution, not directly on the normal distribution. Only when the population variance is known, we can very well make an assumption, irrespective of whatever is the distribution of the population. We can assume that the sampling distribution follows a normal distribution, going with the central limit theorem, right? So what we typically do is, when the sample size is large, though we say will depend on the t distribution, we have to depend on the t distribution. But when the sample size becomes larger and larger, t approaches normal. T is not normal. T is only approaching the normal, which means I can depend on the usage of normal distribution. Right? Only when the sample size is much larger, what we see is the T is going, see, first of all, when the population variance is not known, whatever may be the sample size, large or small, we are saying that we have to use T distribution only. But the characteristic of the T distribution is such a way that as the sample size increases, I see that the T distribution is going to come closer and closer to the normal. So I can approximate a normal distribution to a T distribution. I can very well depend on the standard normal distribution, especially if the sample size is much larger. Right? So that's one alternative. And when the population variance is unknown, and when the sample size is very, very large, I can still depend on x bar plus or minus the z alpha by 2 times the standard error. But if the population size is unknown and the sample size is pretty small, right? If the sample size is pretty small, I have to depend on the t distribution only. And when the population variance is not known, then even the central limit theorem cannot be applicable. But just to understand the properties of t distribution, when I say that this is the typical normal distribution, I see that the t will be slightly flatter and having slightly more tail compared to that of a normal distribution. Right? And what we are saying is, as the sample size is increasing, the t distribution will start approaching the normal, and that's where the normal can be used as a proxy for the t distribution. So whenever we are talking about population variance not known, and the sample size, see, when the samples are coming from the normal distribution, normally distributed population. So here probably we have to look at a few elements. So probably let me mark a grid that makes things easier for you. Sample size large versus small, and we are talking about population variance known, and it's a normal distribution. The population is coming from normal distribution. Variance unknown, population coming from normal distribution. Variance known but not normal distribution. Variance not known and it's not normal. See, first of all, when variance is known and its a population is coming from a normal distribution, I'll look at Z for building the confidence interval. Even if the sample size is small, I'll depend on Z itself. But when I'm saying if the variance is not known, but it is still a population is coming from a normal distribution, if the sample size is large, I can still depend on T, which will approximate to a Z. Whereas when the sample size is small, I'll directly take a T only. But in case of non-normal distributions, if the variance is known, see, I can't do anything for small samples here. If they are non-normal, first of all, variance is known, but the sample size is large, then it is going to approximate a normal distribution because of the central limit theorem. So I'll still rely on Z. But if it is whatever is the distribution, if the variance is unknown, but the sample size is still large, I can go with a T distribution. But again, we are saying that the T distribution can approximate to a Z because the sample size is much larger. So this is what is typically used for the estimation of our confidence intervals, right? So just talking of a T distribution, this T distribution is defined by one single parameter, which is called as a degrees of freedom, which in case of the computation of the variance, it is one lesser than the sample size. So for different degrees of freedom, the T will have different shapes. Probably as the degrees of freedom is increasing, this is what will happen to the shape. So slowly it gets approximating to a normal distribution, but for each degree of freedom, there is a slightly different shape associated with the T distribution. And degrees of freedom is n minus 1, which is playing an important role in finding out even the reliability factor also with respect to the T. And the meaning of this degrees of freedom is how many observations for the computation of some parameter, for the computation of some statistic, how many observations are really independent and how many of them are bounded. So let's say I'm having a sample size of 10 variables, of 10 observations, whose mean is 10. Now I want to see if I have to see the independent observations. Probably I can freely move 1, 2, 3, 4, 5, 6, 7, 8, 9th values, but the 10th value should be guided in such a way that the mean is 10. So the 10th value is typically fixed. It can't be an independently moving stuff, right? Because while computing the variance, first we are computing the mean, and from n independent observations, And now when I'm looking at the variance, only n minus 1 observations can be chosen independently. And that is one of the prime reasons I'll take the degrees of freedom to be n minus 1 and not n. And this is the same logic that is going for computation of the sample variance as well. And coming to the t distribution, whatever in general, when I am looking at a t distribution, we are looking at the samples average minus the population estimated mean divided by s by root n. This is what is the value that is going with the t. And this I can't take it as normal for the simple reason the normal distribution, it involves only the random variable for the mean, whereas the t distribution involves the random variable for the ratio, which is the mean to the standard deviation. So it's a ratio of mean, sample mean and sample standard deviation, whereas the standard normal distribution is a distribution involving only the sample mean. But as we see that as the sample size increases, this goes lesser and lesser and lesser, and that is where it is becoming that is where it becomes more and more closer to z, which would be a measure only of the sample mean and not involving anything to do with the sample variance. So that is one more way of putting up. As the sample size increases, the characteristics of the t distribution are going to be more and more closer to the normal distribution. So sample size is increasing. What we see is one, the peak wise also the t distribution approaches the normal, and even the tails. In normal situation, the tail of a t distribution is higher compared to that of a normal distribution, but again as the sample size increases, the tail of the t distribution also comes closer to a normal distribution. Right? So normally we say t distribution is symmetric, just like a normal, around 0. The mean is still around 0, but it has more and more fatter tail compared to that of a normal distribution. And as the size increases, the tail becomes narrower and narrower. So when I am looking at usage of the t distribution, I have to see that if the population is normal and the variance is unknown, I can use it in all the cases. But if the variance is not known and the population is not normal, I can use it only when the sample size is larger, because as the sample size is getting larger and larger, I see that the sample distribution will be approximated to normal using the central limit theorem. So that's the kind of a mechanism that can be typically worked out. And of course our interval is nothing but x bar plus t alpha by 2 times s by root n, because here I won't have sigma at all. I use s by root n to build the 95% interval around the mean. Now what is very much important is, what are the factors that are typically influencing the width of the interval? We have already seen one is a reliability factor, one is the standard error, and the standard error in turn is represented is a representation of the sample size. So all these things are typically influencing the width of the interval, and whatever the statistic that we are computing, even that is going to have an impact, along with, and the reliability factor is getting impacted even with the confidence level that we are choosing. The higher is the confidence level, the reliability factor is going to be much increasing. So all these various things are influencing the width. So higher is the confidence level, the wider is the interval, The higher is the standard error, the wider is the interval, the larger is the sample size, the lower is the interval that is going to come out. Because the standard error is going to reduce as the sample size is going to increase. So more and more larger samples, standard error decreases. So the confidence interval decreases, and more accuracy comes to the estimate. But the more and more the more and more samples I have to collect, probably the costs are outweighing the precision. So that's where there is a trade-off primarily between the sample size, how large the sample size should be, and the width of the interval, which is resulting in the accuracy or the precision of the estimate. All right. Now, one more important concept that we need to understand with respect to sampling is there are, if I don't select a right sample, if my sample is wrong, probably whatever the estimations that we are making will be completely fraudulent, will be completely not reliable. So there are so many challenges that are there with respect to valid sampling, and those are typically being considered as the various biases that are held as a part of our sampling exercise. So one such one is what we call as the data mining bias. When I say data mining, I completely try to overuse the data, and we try to create our strategies based on some kind of patterns or some kind of distributions that are found in the data. The same set of data we keep mining and researching on it, and the same data we would be trying to extract forcibly so many patterns from the data, so much of interpretation from the data. We do an extensive research on that particular data and try to observe some kind of statistical patterns, significant patterns in the data, and use it as a conclusion for the estimation process. But what could very well happen is that overusage of the data could result into what is called as a data mining bias. So probably it's, let's say I have taken this much of data purely from this period to this period, used it to create a model. Now this model has observed some kind of patterns in the data. Now, based on only the data from here to here, that too of some specific set of companies, that too some specific time period, we tried to dig in too much into the data and finally found out some patterns in the data. Now, using that particular pattern, if I am trying to apply it for the future and if it is not applicable, then it is going to give the results disastrous. So, that is where we talk about an out of sample test, especially if I have used some set of data to build the model. Before trying to apply it over the future forecasts and the future estimates, first try to test them on the past data which is not used to build the model, and see whether more or less similarity is existing or a huge difference is existing. So that is one way to test out the presence of huge data mining bias. And sometimes you see, okay, I'll do some kind of calculations on the data, and based on the calculations I'll take my buy or sell decision. But remember, apart from us, there could be thousands of people who would be doing the same set of calculations, and they would also be getting into the same buy sell exercise. If that's the case, if we are not reacting to it quickly or faster, the others, once they know the strategy, this is no more an advantageous point for us. So we need to know how new it is. So we can't rely on the same set of models, same set of calculations for a longer period of time, which could really bias our estimates altogether. So too much of digging into the data probably may result into a too little of a confidence while developing the estimate, and that is what we are referring to as the data mining bias. And at the same time, our sample may be very much subjected to a sample selection bias. Means when I am selecting the sample, I am not selecting it, let's say, in a random fashion. I am more and more biased towards the selection. Right? When there is some kind of a bias, or when few values are intentionally omitted or intentionally included, that is where the sample selection bias is coming into picture. In some cases, probably I am omitting it because of data availability issue. Though I have selected that I will take the data of this particular company, but because I am not able to collect the data of this particular company, I have omitted it from my analysis. So even in those cases, we will not be able to get a better estimate because the samples that we have collected, they are not completely random. I had to change the sample because of unavailability of the data. And on the same lines, there is one more improvement which is called as a survivorship bias, which says probably let's say I have included, I'm talking about the performance. I'm talking about the performance of companies in 2014, right? And so here, when I'm looking at the performance of the companies in 2014, probably let's say I'm doing this analysis in December 2014. Now, whatever the companies that are there in December 2014, if I take a sample from those companies and I try to do some calculation, the numbers could be different. But if I go with the companies which were there even on Jan 2014, some of them would have gone completely into losses and completely winded up by December 2014. The performance of those companies is not taken into consideration, then probably my average, which I am defining through the December 2014 available data, would be much higher than doing the same with the January 2014 available data. So whenever we are looking at, okay, we are omitting because the data is not available. When I'm trying to take some financial ratio of a set of companies, just because one company has not published its financial statements yet for the current year, I am omitting that particular company and including some other company. All these things are the result of sample selection, and if any particular omission is because of that particular entity not existing anymore, it is giving more and more towards the survivorship bias. So that's also one serious problem that we quite often encounter. Then we are talking about a look ahead bias. So any data that I am planning to capture at a particular point in time, it is not available. So I am taking a previous data for doing my analysis. So whatever the analysis that I want to make, it is not available on the test date, so I have taken a previous data. So that kind of a bias is going to be what we call as the look ahead bias. My estimate will get suffered because of that. We have to be very careful about the look ahead bias in our data. Then I am also talking about time period bias. How long or short should be our time period? If the time period is too short, probably I cannot use the data to make a general prediction. because whatever the data that we have captured could be more of a reflection of this small time period where the economic status could be in some specific format. So the small time series may not give a generalized or a long-term behavior, but it is more and more specific. But if I am taking a long-term period, probably a picture could be more and more realistic. But in case any kind of structural changes happen, probably in the last 5 years the economy has opened up and something else has happened, but prior to that it was, let's say, a closed kind of an economy. In those kind of scenarios, even a very long term data may not be of any kind of a help, because they are the data whatever we are pulling, they are from two different kinds of distributions altogether. Prior to this, probably the distribution could be different because of a structural change. After that, the distribution could be something altogether different. So that is one of the prime reasons we have to be very careful with respect to the bias. And just to add something to the survivorship bias, especially when we are not able to take the data of the companies into account because they have either gone bankrupt during that particular period, winded up their operations, they have got merged into some other firm and their data is not available, and I'm not considering them for the returns analysis, whereas last year I have included them. That is what is going to give me a kind of sample selection issues, and survivorship bias is going to be said to prevail in that particular situation. So in totality, what I wanted to discuss was we need to be very careful with respect to the sample that we are selecting. We need to have a detailed amount of idea regarding the sample, what is going into that particular sample, how the sample has come out, because the sample is the starting point for any kind of computation, and thus taking it forward further towards estimation or doing some kind of hypothesis testings and providing some conclusions about the data. So that is what we are trying to look at when we are understanding this particular chapter. So if you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.